Okay, class, me again. Yeah, I got a question here about number 13 and a couple other questions too. I'll do those soon. But this one is, and I guess I should just read it. It says, what is the gravitational force between two 20-kilogram iron balls separated by a distance of a half a meter? Now, that's the first question. The second question says, how does this compare with the weight of either of them? Let me hold off on the second one and just point out that this chapter is all about the universal law of gravitation, which just simply says this, that if you want to know the force between any two objects, and that's kind of important here, because I think sometimes we think about the force of gravity as only the interaction between ourselves and the Earth. But what Newton is trying to say here, and the reason we call it universal, is it doesn't matter if it's the Earth. It's just any two objects. So you could say, what's the gravitational force between you and your car? You and the Earth is probably the bigger of them and the one that's relevant, but you would have a gravitational force between any two objects. You could say, well, what's the gravitational force between your fridge and your stove? And you'll see that these are small numbers. That's the second part of this. So really, the main thing we really often only care about is the gravitational force between, an object and the Earth. So the fridge and the Earth, or me and the Earth, or the oven and the Earth. Between the fridge and the oven, it's just way too small. But nonetheless, it is universal, and that's what this chapter is about, to teach you the basic physics. And so let's calculate this. So I guess I'd put in this number, 6.67 times 10 to the negative 11. Now remember here, the units are newtons, meters squared, and kilograms squared. That's kind of the catch to say then you better make sure you then put in your mass in kilograms. And this one was given in kilograms. So the first object is 20 kilograms and the next object is also 20 kilograms. Okay. Now they're kind of close together, a half a meter. Okay, so I'll put 0.5 meters. But again, watch your units because it needs to be in meters. And so they did that. So there was nothing tricky about the units this time. But sometimes they'll give mass in grams, and I got to watch that. I got to go to kilograms. Oh, they'll give distance in centimeters, and I need to watch that. But for this one, you can just see that the kilogram, two of them up here, would make kilograms squared and would cancel with that. And then this, the meters squared here, would cancel with the meters squared, and you'd just be left with units of newtons, which we should since it is a force. So then I can just grab my calculator here and go, okay, 6.67 times 10 to the negative 11. I can multiply by the first 20 and then multiply by the second 20. Then divide by the half a meter squared. And I get a number that, as you're going to see, is really quite small and not even really noticeable when you compare it to the weight of the object. So again, you don't really notice these kind of things. You never think about the force between the fridge and the stove. You think about the force between the fridge and the Earth and the stove and the Earth, especially if you've got to move them and install them, and that's what matters. You've got to overcome that force. That's the dominant one. All right, so this is a really small force, and so two lead spheres here would be pulling on each other, and they would come together, but it'd be very little. And compared to their gravitational force pulling them down, you wouldn't even notice this. And so let's do the second part of this, which is, how much is it pulling you down? And so we need to go back a chapter or two and just remember that the weight of the object is mg. So this is 20 kilograms. And we can do 9.8, or if you like, you can even round it to an even 10. I'll just round it to an even 10, because then it becomes 10 times 20, which is 200 newtons. It technically is a little lighter than that. It's 9.8 times the 20. What's that? 196 would be a little more accurate number. But either way, it is way bigger than this. Remember, this means, 7 zeros here. So this is, 0.00000. 1, 2, 3, 4, 5, 6 zeros, then a 107 newtons. And when I'm comparing that to, 196, and it's just not even close. This is 7, 8, 9 zeros. This is a billion times. This is a billion times bigger than that one. And so that's what they're trying to get you to see, both of these, that, hey, it's universal. You can calculate it between any two objects, but things like lead spheres and refrigerators and stoves are pretty small compared to force of gravity. And so we often ignore it, pay little attention to it. We should study it because it's part of the physics. But again, if you're trying to move things around and it comes to engineering, you don't need to consider those. Consider the weight of the object only, not the interaction, So you got two big blocks of concrete when you're installing a bridge. The engineer just worries about the weight of those blocks of concrete, not the force between the two pieces of concrete. It's just too small to consider. Good science, but also it's good to know the numbers are small and not needed compared to the weight of them. That's kind of the point here.